Okay, so before I begin, I would like to thank all the organizers for giving me the opportunity to stay and work here, and also to give the talk in this conference. So, so the topic of today is torsion in the Chow groups of zero cycles. So, basically, I want to study the torsion in these Chow groups. So, so what is the question here? So it's a very general question. So let X be a smooth projective variety. So, so let's fix an algebraically closed field K of any characteristic. So you have a smooth projective variety of dimension D over K. Then question is, what can we say about torsion in these Chow groups? So I don't think it's an easy question. So, so it depends on what codimension you choose. If you take codimension 1, it's very easy. And if you take other codimensions, we don't know. We have nothing to say here in the middle dimensions. So here in this talk, I will consider say these groups, the zero cycles, which sometimes I will also write like this. So in the middle of the talk, if suddenly I switch from here to here, do not get confused. Okay. So here, the most remarkable theorem, as I see it, is the theorem of Brightman. It says that the prime to P, where P is the exponential characteristic of the field, torsion in CHD of X coincides in the loose sense, means there's an isomorphism with the prime to P torsion of an abelian variety. So it's a very nice description. It tells you that you can estimate the torsion subgroup of the Chow group of zero cycles. And this abelian variety is, as you can guess, is nothing but the Albanese variety of X. And this theorem of Brightman was generalized by Milne, where basically you do not need this. It's true in general. So general in this sense that you can remove this condition. So in particular, all torsions in zero cycle group is isomorphic to the torsion in the Albanese variety. Okay, so after Brightman proved this result, Spencer Bloch gave another description of the torsion in this Chow group, and his theorem is the following. He says that let X be as above, and let L be a prime different from P. So, yeah. So I did not write P. P is assumed to be the characteristic of the base field. Then there exists an isomorphism namely, you look at this group and look at the L primary torsion. So this is the L primary torsion subgroup. And he gave a canonical isomorphism which he denotes by lambda x into some étale cohomology. X, and then this is QL more ZL twisted by D. So it's a very explicit description of the prime to P torsion in the Chow group. And actually, as I understood the proof of Bloch, this construction, there is no canonical, actually natural map from either in any direction. So the most complicated part of the proof is to construct this map. I think his proof uses, in fact, the construction uses some part of Well conjecture. Okay. So this is what we can say about torsion in the Chow group of zero cycles if X is a smooth projective variety. And it's a consequence of this theorem of Brightman and Milne that the following holds. If X is affine, implies that if X is a smooth affine of dimension D bigger than or equal to 2 here, then actually you can say a very nice thing. You can actually this group is torsion free. So if X is affine, actually this Chow group has no torsion at all. And here this is very crucial that dimension must be at least 2, and easy to see that in dimension 1 this cannot be true. Okay. So sometimes this is often called as the affine Reutemann torsion theorem. Yes. Sorry? You don't need a resolution of singularity. No, we don't need resolution of singularity in any statement till now. Yeah.
How do you embed the smooth affine in the smooth? Yeah, that's my question. How do you embed this affine scheme?
Well, you do not need that. The idea is to reduce to the case of surface, where you do have resolution of singularity. Okay. That's the idea. Okay. So it's a good question. I also initially thought that what's going on, but the idea is to reduce to the case of surface. Okay, so we can move this up. Oops. Okay, so this is all we have for a smooth variety. Now, my objective is to understand these questions if X is not smooth. So what can you say in general? So the question is, what happens to the theorems of Bloch and Reutemann's Milne? Actually, I have noticed that often in the literature, people say this theorem of Brightman, they never say Reutemann-Milne, but so, I may also sort of abuse this thing, and I may often say, what is Brightman-Torsion theorem? So what happens to these theorems when X is singular? So, for the question is, well, what is the Chow group here, first of all? So we are talking about the torsion in which group? So the obvious the thing which comes to our mind is the Chow group defined by Fulton, namely the Chow group of zero cycle. But that's the wrong definition, because that definition is a homological definition. It's like, like if for a smooth variety, you have the Poincare duality, which tells you that whether you take K theory or G theory, they are isomorphic. So if you do not have that, then the Chow group which you see in Fulton gives you G theory, not the K theory. So what I am concerned here is the Chow group, which allows you to detect elements in the K group, namely the K naught. So it's not Fulton's Chow group. So we have the Chow group of zero cycles, which namely I will denote by CSDX, which I will try to define at some point of time, but which basically corresponds to K naught of X, not G naught. Here I have to make a difference because X has singularity. And this definition, one of the authors of this definition is sitting in the audience, and this definition is due to Levine and Weivel. Okay, so they gave a definition of, at least for zero cycles. Conjecturally, you can ask what happens for higher dimensional cycles. There are definitions, but they are tremendously complicated. So this itself is complicated, but so this is the definition due to Levine and Weivel. So in brief, what is this group? It's exactly like in the smooth case, you take the free abelian group generated by zero cycles, the closed point, but you do not allow closed point which lies on the singular locus of X. You take only closed points which lie on the regular locus of X. That's fine, but what's the relation? So relation here, you take exactly like in the smooth case, you take curves and take rational functions, and then you take the divisors. Those are the rational equivalents. But here you have to make some difference, namely, you cannot allow arbitrary curve, because the curve should have class in K naught. So if you take arbitrary curve in X, then it's not a local complete intersection. So you demand that your curve along the singular locus is a local complete intersection. That's one condition. And then other condition is you take only those rational functions which are regular along the singular locus of X and invertible, so that they have no poles of zero, because you do not allow those points in the zero cycle group. That's it. So if you take these two conditions in mind, then the definition is exactly like in the case of Fulton. So that's the definition which I will not write down. Simple definition. So in general, there are some issues that in general you are supposed to take non-reduced curves also, unlike in the case of smooth varieties. But there are some Bertini theorems which tells you that if X is reduced, then you may not be able to take irreducible curve, but you can only choose reduced curve to define rational equivalence. Sorry? No, it is not. It is not birational invariant. That's a kind of subtle point. So often, one of the questions in this theory of singular variety, understanding the Chow group, is you have a canonical birational invariant, namely the resolution of singularity, and you try to compare and see what is the defect, and defect somehow gives you some information about the singularity of X. So it almost is never birational invariant. So so that's the point. So such curves are often called the Cartier curves, which I will use from now on the rest of the talk. So the Cartier curve is the curve which gives you rational equivalence for zero cycles here. Okay. So now once you have this group, and it is, of course, I should also tell you that already, thanks to Levin and Weivel, they kind of gave enough evidence to say that this group is indeed, if you have some nice filtration over here, then this should be the smallest piece of that filtration. So this is indeed supposedly the right Chow group. And there are various theorems which indicate that this is indeed the right one. Okay, so once we have that, so we can ask these questions now, that namely the question of Brightman, Milne, or Bloch, is any of them true? And in the complete generality, the answer is we still do not know what happens. So the answer to this is, in general, we do not know. So in general, but in special cases, there are some results, and let me just indicate to you. So in characteristic 0, we do have Brightman theorems. We do have Brightman. They know Milne here because they know characteristics, Brightman's theorem. And they know positive characteristic here. And this is due to various people. In dimension 2, this is due to Barbieri Viale, which I write as B. Often, I am used to their papers. I often write like Barbieri Viale, Pedrini, and Weivel. This is in dimension 2. And in general, in higher dimension, this is due to Biswas and Srinivas. And this is very involved, actually, this proof, even this proof and this proof uses the theory of, this proof uses mixed Haus structures, this uses the theory of Haus modules of Morihiko Saito. Okay. So you have this, and positive characteristic, we don't know anything, what happens. You have no results. Yeah, so I am actually wrong, I am forgetting my own result. Okay, so in positive characteristic, we do have Brightman Torsion theorem if X is normal. And this is due to myself and Srinivas. But, yes? Yes. This is in all characteristics. That's the point. And I should say here that if X is normal, this theorem of Barbieri, Viale, Pedrini, Weivel, or Biswas, Srinivas were already known by Levin. So their theorem, these people do it with arbitrary singularity. If it's normal in characteristic 0, it was proven by Mark Levin. And here, if X is normal in positive characteristic, this holds.
But you have also Albanese?
Yes, you have Albanese. Yes, it's Albanese given by Lang. Yes. It may have, no, it has no LT part if X is normal. No, in fact, it's an abelian variety. It coincides with the abelian variety of the any resolution of singularity you can have. So it's an abelian variety. If X is normal, but in general, it will be, if X has arbitrary singularities, there is an Albanese by Ellen Eckhart Vivek, and V. Srinivas, that may have all sorts of bad things. Additive, semi-abelian, abelian, everything. Okay? But if X is normal, all these things vanishes. Okay? So, this is what we have. But what happens to the theorem of Bloch? We have no idea. I don't know how, I have no, I would like to prove it, but I don't know how to prove it. But I will tell you, in some cases I can prove this. So that is the part of this talk. So what is the, okay, so here is the main theorem now. Let me write a main theorem for today. This theorem says, remember that one of the consequences of Brightman's theorem for projective variety is the affine Brightman torsion, which tells you that for a smooth affine variety, the Chow group of zero cycle is torsion free. So you can ask, what is the, is it true for singular variety? And that's the main theorem. Theorem is that let X be a reduced affine a scheme of dimension d bigger than or equal to 2 over k, then CHD of X is torsion free. So this is the main theorem of today, that at least you can actually prove affine Riemann torsion for all singular varieties in all characteristics. Okay. And this theorem has several consequences, so which I will tell you now. So, so let me write down some applications. So it turns out that like now I can prove Bloch's theorem for at least for surfaces and some kind of in higher dimensions, and even that surprisingly uses this theorem, this torsion theorem. So it's kind of in part of this torsion theorem, the proof of this torsion theorem. So kind of it's surprising to me that how, although Bloch never uses this Riemann torsion theorem. So, so first step, okay, so let me give you, so there are applications on the algebraic side, sort of like almost arithmetic side, and also in geometric side. So let me give you these applications. So the first is on the algebraic side. So this is part one. So here, there is a, so let FD, so from now on, X will be, X is always affine because this main theorem is for affine. We define FD K naught X as the subgroup of K naught X generated by a smooth closed points. Remember that because this point is smooth, it has a class in K naught. So I can take the subgroup of K naught generated by these points. That I denote often by FD K naught. And then once you have this, there is a conjecture of Murthy, which says the following. Conjecture is that FD K naught of X is torsion free. Okay, Murthy had some interest in this conjecture. In fact, if you see the annals paper of Murthy, which was mentioned by Hausdorff yesterday, he proves many fantastic theorems in that paper. And most of his theorems, actually, if you see, is based on this assumption being true, that assume that it has no torsion. And it turns out that this conjecture, so the theorem, one corollary is, let me write it as a theorem, 2, that Murthy's conjecture is true. Okay, this follows from that theorem. Okay, so what is the consequence of this theorem now? So here is actually already in yesterday's talk, in Hausdorff talk, he explains one conjecture of Murthy, namely if you have vector bundles, if you know the sufficiently many Chern classes which vanish, then can you say something about vector bundle having a lot of trivial subbundles? So that's the main philosophy of Murthy's thing. So now I am interested in this question for vector bundle of rank D. As Hausdorff yesterday said that if the rank of the bundle is bigger than the dimension, this is a theorem of Sayre that it always has a trivial line subbundle. But what happens in dimension T? So here is a theorem 3. Let X be as above, okay, and let V to X be a vector bundle of rank D. Okay, then it turns out that this vector bundle has a Chern class in that Levin-Weibull's Chow group, top Chern class. And this construction is due to Mark-Levin. Okay, so it has a top Chern class. So then this is the theorem is this is 0 if and only if V has a nowhere vanishing section. So what this theorem says is, this theorem generalizes the theorem of Murthy to singular variety. If X is a smooth, this theorem was proven by Murthy in that Annals paper. And it turns out that actually Murthy's theorem generalizes to all affine varieties. Okay? Sorry?
What is the right condition here?
The rank D is equal to the dimension of X. So I'm taking bundle of top rank.
The word is rank.
Sorry?
It's the word rank.
I see. Okay, this is this. So okay, rank of V. So let's, okay. Does that make you happy? Okay. So this is so you can say this. So here I should mention because I am studying singular varieties, there is a theorem of Marcus-Listing which says that which proves something similar without any condition on the base field, but not in this form. He doesn't have this Chow group here in the Chern classes. He has some very abstract kind of class in, I will mention here.
Is there a map from this group here to my group?
Sorry?
Is there a group map from this, the Levin group to my group?
I am coming to that. Okay. So, so Marcus-Listing proves that something similar happens. So V as above, V and X as above. Then V has a nowhere vanishing section if and only if. So he proves that it has a this bundle has what is called Euler class in some group which he defines as this. He says we can take Nishnevich as well. X K M D. Remember that because I am over algebraically closed field, I don't write W here. In general, you have to take Miller-Witt shape. Okay, so he says that this happens if and only if this is 0. So now it's a natural question, then how do you compare this result with that result? Okay, there I take the Chow groups and take the Chern class. The Chern class is very easy to define actually. So you can very explicitly say that when it bundle has no vanishing section. But this class, Marco defined using some homotopy groups. And then, so what can you say about this? Is something very abstract. We have no information about this. You don't know how to compute this because there is no Gaussian resolution because X is singular. So how do you compare? So that brings me to my another theorem, which I will, here is a theorem that let X be as above, then there exists what I call the Bloch-Quillen formula. namely that there exists an isomorphism from CSD of X to HD Nisnevich X KMD. Okay, so you can prove Bloch formula, and I should tell you that interestingly, this proof of Bloch's formula also uses that main theorem. Okay.
Now, Steve, does it mean that, because mine also works with the Zell's topology.
Sorry?
Does it
Yeah, the difference is that I do not know how to remove this and put Zariski here. I believe it's not true. There is a surjection from if I replace Zariski to here, but I don't know how to prove that is injective. So I can prove this, that if you replace Zariski by Nisnevich, then this is exactly the analog of theorem of Bloch and Cullen. Because you have the Bloch formula. Okay. And I should tell you that there is a ongoing work where you can prove something similar if K is not algebraically closed, where you have this group where you take Milnor-Witt, but here you take some kind of Chow-Witt group which is defined using some cycles, not like in the abstract sense of what Hornbostel was saying yesterday. So that's for normal I can kind of see it, but I want to see how it works for arbitrary singular variety, and the thing is that it should work. Okay, so this is you have this. So this is about Murthy's theorem. Now another application is the following. Again, I am in algebraic side. Okay. So in commutative algebra, there is other questions which often arises is if you have a variety and if you have a closed subvariety which is a local complete intersection, when can you say that subvariety is a complete intersection? This is like a very, very classical question, and of course very hard question. So there are some. So here is and this. So the study of projective module and a local complete intersection being complete intersections are related. So the one application which I can prove is the following. So here is a theorem. Let X, so let me write here like in algebra, let A be a reduced affine algebra of dimension D at least 2 over K. Let I contained in A be a local complete intersection, this complete intersection ideal of height D. So in general, for any height, you can ask, can you give me some conditions which implies that this ideal is a complete intersection? And I can answer this for height D. That the answer is that if this is a local complete intersection of height D, then the theorem is then I is a complete intersection. If CHD of A, I should write it more carefully, spec A is 0. So if you have an affine variety whose Chow group of 0 cycle is trivial, then this is universally true that every complete intersection ideal of tau codimension is a complete intersection. Remember that this is kind of a bit subtle because you see that this ideal may have support in singular locus. It may have. But on the other hand, the Chow group doesn't include those singular points. But somehow still you can conclude this using some sort of Botany theorems of Swan and Murthy. So in particular, this has a consequence. In particular, here is a theorem. If you take K equal to the algebraic closure of a finite field, okay, suppose you take this case, then this happens. Then this happens. Yes?
I is a complete intersection if the child group of spec A is 0.
Yes, if the Chow group of spec A is 0,
That hypothesis has nothing to do with schedule I.
no, I wrote it. In my mind, I forgot to write this before, then I added it. But this, assume that this happens, then every local complete intersection of height D is a complete intersection. So it's kind of the theorem is written a bit wrongly. Yeah.
You're going to say the follow-up about the Chern class of the element in general?
Sorry? Yeah, that's right. Yeah. So in general, what happens is, you're right. Yeah. Thanks to Chuck, he corrected me. So basically, you can generalize. You can say the following: that if you have a complete local complete intersection ideal of height D, it has a class in the Chow group of 0 cycle, and this ideal is complete intersection if and only if that class dies. So that does not require the universal condition on the Chow group. Okay, that's the correct formulation. And actually, that theorem also requires to know that there is something called Euler class group defined by Bhattacharya and Sridharan. And that Euler class group has this property, which I said, if you have every ideal which is local computation, it has a class, and this class vanishes and if and only if this happens. Then how do I conclude this with my Chow group? And for that, you need to prove that that the Euler class group is isomorphic to, so basically, I didn't have time. The point is that this is isomorphic to the Chow group, I have already said, and this is also isomorphic to the Euler class group of X. This is in the sense of Bhattacharya and Sridharan. So my point is that if K is algebraically closed, the group used by Marcus Listing, the group of Levin-Weibel, and the group of Bhattacharya and Sridharan, they're all isomorphic. Okay? Yeah. So then this happens. Why this happens, again, uses that main theorem. Because it's not difficult to show that if you have a affine variety over the algebraic closure of a finite field, Chow group must be torsion. Right? On the other hand, my theorem says that it cannot have torsion. So it must be 0. So, and then you can, then it tells you that over finite field, algebraic closure of finite field, every affine variety, if you take local complete intersection of the top height, then it is a complete intersection. So this is what I call my almost arithmetic applications. Okay, in the context of the title of this conference. Yes?
You also have a set theoretic complete intersection condition, not just a local complete intersection?
No, then only,
If it's torsion free, then that's automatic, isn't it?
it's not clear. I thought it's not clear to me actually. So maybe you can explain to me how it works. Okay, so I can say this. Okay, so this is the applications in. There is another arithmetic application. Let me just give you very quickly. Namely, so if you remember, there is a conjecture of Bloch and Belinson's which tells you that if you have a smooth affine variety over a number field, then its Chow group must be finite. Chow group of 0 cycle. Right? This is a kind of consequence of Bloch-Belinson conjecture, which we don't know anything about. So if you think about that, then you could ask that what happens. So let's take CH of D of some X. Then, if you think of that, then if you take a smooth affine variety over the algebraic closure of number fields, Q, namely Q bar, then it should not have Chow group, right? According to Bloch-Belinson conjecture. Because it's supposed to be torsion free, on the other hand, it's supposed to be torsion. So, but do we have some examples? So here is one example which I can give you. This is the example due to myself and Srinivas, that let A be a graded affine ring, of course reduced, over Q bar. Okay? Suppose I allow is graded. Then I have lots of examples of Bloch-Belinson's conjecture. But with singularity, that's a kind of a strange thing. Then this does happen. the Chow group of zero cycle vanishes. So in particular, every local complete intersection of height d is a complete intersection. Okay.
Does it have something to do with Q bar?
Yeah, it has something very strongly to do with Q bar, yes. Because first of all, one important thing is that differentials vanish, there is no differential, relative differentials, and that's the main point actually. So at least in our proof, that's the main point we use. And it's not surprising because you see geometrically, if you take the spectrum of a graded ring, it should look like a cone. So you believe that this should be true, it should be contractible, and it does happen somehow. Okay. Okay. So this is like, these two are kind of my almost arithmetic applications. Okay.
I'm confused. Why is it not true for other algebraic closed fields?
Which one?
The last example that you used.
That the Chow group is 0?
Yes.
No. That is, I don't think that's true.
Yeah, but every pointer can be.
A Chow group is arbitrary. If you take complex numbers, no, it could be very big. It could be like uncountable.
Every pointer is rational equivalent to the vertex of the cone.
Yeah, but yes, that happens, but the cone cannot be non-singular because the cone has the singularity at the vertex.
There's an obstruction formally with scalar differentials in the field. And if the field is Q bar, the scalar differentials are zero. That's 1
Okay, so I have like 20 minutes, so let me give you in another few minutes some more applications, and then I will try to see what proof I can sketch. Actually, because I thought that in this audience there are people who are not really like familiar with this subject, so I thought I should, rather than giving the full details of the proof, give you some kind of like, some very like chaotic survey and also some theorems in these directions. Okay, so keeping that in view, let me give you some now geometric applications. So the first application is the Chow group with modulus, which is these days my favorite subject, Chow group with modulus. Okay. So what happens? So this was already defined by Romeo Ivasas. I don't have to define it. Actually, sometimes it's always often good to give lectures towards the end of the conference because sort of like you can like save from writing various things. So this was defined by Ivasas. I will not recall. So, and as Rumi explained that the main point, one of the point of this Chow group of modulus is to give some kind of motivic description of the relative K theory for a smooth variety with respect to some effective Cartier divisors. On the other directions, there are other applications, namely suggested by the theorem of Morris-Kurz Saito is that often suppose you want to understand something about an open variety with some condition on the, if you take the compactification, nice compactification, if you put some condition on the boundary, then does the Chow group with modulus capture this kind of information? In particular, like what Kurz Saito do is that if you take some étale covers of that open thing with some fixed ramification along the divisor, can you cover this using some Chow group? And they do cover, they do describe in terms of Chow group with modulus. So it's a very nice theory, but on the other hand, extremely complicated as I see it at this stage. So, although definition is simple, but it's like, so what is the application of my theorem here? So here is the application. Now you look at the Chow group of zero cycles with modulus. So this is my this is a notation I suppose used by Romeo that you. So this is a Chow group of zero cycles. This was already defined by Kurz and Saito with modulus D on a smooth, affine variety X of dimension D bigger than or equal to 2. So let's take this group. Now you can ask the same question. My title of the talk was the torsion in the zero cycle groups. So there are various zero cycle groups. One of them is this. So you can ask that, can you prove some Reutemann torsion theorem, affine Reutemann torsion for this? And it turns out that that main theorem implies this also. So here is the theorem that with this modulus pair, which Romeo calls it, as above, it turns out that CHD XD is torsion free. Okay, so you can prove affine Reutemann torsion for cycles with modulus as well. This is also a consequence of, so here comes the sort of connection between cycles with modulus on a smooth variety and cycles on singular varieties. My main theorem was cycles on singular variety, here is cycles on a smooth variety. And it turns out that they are related. And this was the theorem of myself and Federico Binda, where we proved that there is a very strong connection between these two. And I used this result and that strong connection to deduce this theorem. Okay?
What's the hypothesis on the divisor?
No hypothesis, any effective Cartier divisor on X. Okay? So in particular, this may be highly non-reduced. So it may have like lots of p torsion in general, right? You expect. But the point is that it has no p torsion also. Okay? So, yeah, so this is, now, so this is all about the affine Reutemann torsion theorem. Now, finally, let me give you the analog of Bloch's theorem in general. So here is the analog of Bloch's theorem, which I cannot prove for all singular variety, but what I can prove is the following. So here is a theorem, let X be a smooth projective variety of dimension d in no condition here over K. Let D contained in X be an effective Cartier divisor. Then the following happens. Then the conclusion is there exists an isomorphism, namely, look at the for, as before, for L not equal to P, A prime. Look at Chow group of zero cycles with modulus and L prime retorsion. Okay? Then there exists an isomorphism which I write it as lambda xd to étale cohomology of x related to d and here ql mod zld. So this is what I can prove. I don't know how to prove this for all singular varieties, but I can prove this theorem for all singular surfaces. The idea of the proof is this. I can prove this Bloch's theorem for all singular surfaces. And then I sort of use induction and doubling trick to prove this theorem with cycle with modulus for all projective variety with all effective divisors. Okay? Sorry?
Right-hand side,
Yeah?
independent of the multiplicity of D, it only depends on the reduced power of D.
Yeah, it's a consequence of this theorem. A consequence.
Right-hand side, on the étale
Yeah, it does not depend on the multiplicity of D on the right hand side. Yes. So as a consequence, it tells you that even the left hand side does not depend. That's the consequence. So one consequence of this, one application of this theorem is that if you look at the prime to p torsion in the Chow group with modulus, that does not see the multiplicity of the divisor. Okay, that's the consequence of this theorem. Okay, but if you take p torsion, then of course it's like, I don't know, it's really, I cannot say at this moment what happens. I think the problem, as far as I see, the problem with P torsion, we cannot say much about P torsion in this case for projective variety is the problem is the Albanese variety of Eno Srinivas and Vivek. It exists, but it's very difficult to study what it is. So there are works by Russell in this direction, and I'm trying to study those works, and I hope that it's still looking very complicated, but the problem is that the P torsion in that Albanese is some, no idea what happens.
Can I ask on the previous theorem here, can you replace the assumption x smooth affine and d divisor in by x affine and smooth and d is a divisor at infinity, with some Cartier divisor in some normal compactification?
You mean in this theorem?
Not the last one.
In the first one?
Yeah, the previous one.
So you mean that the divisor is not hitting the affine part?
You have x, I mean what happens for many programs, x is smooth affine.
Yes.
But your divisor is not on x, the divisor
It's on the compactification.
at infinity.
Yes.
It's a non-part divisor at infinity, which is Cartier.
I don't know if I can prove that, and I am a bit skeptical of this in that case. I don't believe it will be true. I think it will be it will have torsion. I think so. So okay, so this is the analog of this is exactly the Bloch's theorem for cycles with modulus. Okay, so now finally I should, as the tradition says, I should give you some proof. Okay, so in last 5 to 6 minutes, let me give you some sketch of okay, so a very brief sketch of the proof of main theorem. So okay, so how do you prove the main theorem? Namely, the theorem is, let me recall, X is a affine variety of dimension d at least 2 over an algebraically closed field. I want to prove that it is Chow group of zero cycle has no torsion. So how do I prove that? Well, let's take any alpha in the Chow group. Let's say this is a group of zero cycle, and such that some n times alpha is rationally equivalent to 0. This is what is given to us, right? I want to prove that alpha itself is rationally equivalent to 0. That's the point. So how do I prove it? Well, so the idea is to use induction on the dimension and again eventually reduce to the case of surface. So this is how you prove even for smooth varieties. So how does, well, so what does that mean? That means that there exists a Cartier curve, reduced Cartier curve, a C and a function, rational function f on OCX singular star such that the divisor of f is equal to n alpha, right? This is what it is. So now the trick is that if I can produce a surface, complete surface in X which contains this Cartier divisor such that in that surface this is also Cartier, then I am done if I know for surfaces, right? But the problem is that if I take an arbitrary Cartier curve in X, it may have some very big embedding dimension, right? Because dimension of the variety may be very big, so the embedding dimension of the curve may be also much bigger than 2. So that it is impossible to, in general, cover this C inside some surface. It's not possible. So what do I do? So the idea is, again, this is the trick due to Bloch, which he plays in case of a smooth variety. He says that you try to blow up. So what I do is that I try to blow up, so remember the C is reduced. So I try to blow up the points of X along some points of C, such that by blow up, I can make C, the strict transform of C, sufficiently nice so that the embedding dimension becomes 2. You can always do that. Okay? So after blow up, I make the embedding dimension of C 2, at least along the regular locus of X. Once I have done that, then I can, this is a theorem of Altman and Kleeman, that if the embedding dimension is sufficiently small, I can find a complete surface inside that blow up, which contains this Cartier curve, and remember, this cycle can always be lifted. So I lift this cycle over there, and then over the blow up, I find a complete intersection surface, where this becomes, a strict transform becomes Cartier. Then you kill that cycle there, and then you push it forward, and then you kill it. So that's the idea, okay? So you do some sufficiently many blow up, you do blah, 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 and then you then you push it forward. So then eventually it reduces to, remember that there is a catch here. It reduces to proving this theorem is not enough to prove this theorem for a fine surface, because I have blown up. So I have no more than a fine surface here. So I cannot simply say that it reduces to case of a fine surface. I have to prove much more than for a fine surface. So eventually it reduces to proving the following lemma. This is what it suffices to prove that. Let X be an affine surface, and let F X tilde to X be a blow up at a finite closed subscheme such that X tilde is a smooth finite closed subscheme, let me put it Z inside X, is smooth along Z. In other words, you are assuming that, which suffices in this case, that when you blow up the surface, then the point where you blow up, the blown up surface is smooth. In other words, that this surface X tilde is a resolution of singularity of X, not everywhere. It's a partial resolution of singularity in the sense that it has no singularity over this G. Okay? It may have singularity away from Z. Okay? So this is like closed subscheme Z in X whose support is 0 dimensional. That's what I am saying. Okay? So then, if it happens, then the claim is that the Chow group of X tilde. Actually, in my theorem, I did not say that. The point is that the Chow group is not only torsion free, but it's actually uniquely divisible. It's a Q vector space. So this is also uniquely divisible. It's not only torsion free. What is?
What is Z?
This is a closed subscheme along which you blow up X.
It's close point. I mean, it's second close point.
Yeah, but it may have nilpotent. I am not saying that I am just blowing reduced. I am not saying that. I cannot guarantee that. I am blowing up some closed subscheme whose support is finite. That's all I am saying. Okay? I am not saying it's a closed subset. It's a closed subscheme. Okay? So you reduce to proving this. And the proof of this is essentially, first I prove for X, and the proof for X tilde is it requires some more argument. So basically I just give you the sketch to prove what happens for a fine surface, not for the blow up. Let me just give you just 1 minute I should take. If I am allowed to take just 1 minute, let me just give you how do you do for X surface. Here what you do is that you normalize the surface. Okay? And then you can write down some kind of a conductor like a square, and then you can write down some exact sequence. Remember, if you allow the conductor scheme to be like sufficiently high nilpotent, then you can write down an exact sequence. That's the point. So you write down, and then you remember that because you are in the affine scheme, because you are in a affine situation, for a curve, the SK1 doesn't see the reduced or non-reduced. You use that. And then you use the fact that for normal affine surface, I already know this theorem. That is by myself and Srinivas, which I said in the beginning. So then if you write down this usual like 5 lemma, you are reduced to proving the following theorem, which is itself not an easy theorem. That's the reduced to proving the following, some kind of hard theorem, is that let X be an affine normal surface over K. Okay, then you reduce to proving the following. Then look at the SK1 of X, and you take tensor over Z, Q mod Z, then this is 0. Okay, if you prove that, then if you write down the exact sequence, blah blah blah, you will see that you are done. Okay, but this is a non-trivial theorem. This requires, let me just say, this requires first a CDS descent for K theory. And this is only for the normal surface, which I had already done long time ago, even before Matthew Morrow. So use that. Then you use some results of Hesselholz and Geisser, which give you like that many of the relative K theory have bounded P torsion are bounded exponents. So use that. And then you use some theorem of Geisser and Levine on the K theory of smooth varieties. On the P torsion in the K theory of smooth variety, there are some results. Use those results, and then you conclude it. This is a kind of non-trivial theorem. And that's how you conclude the proof. Sorry for going extra time. Thank you again. Yes?
So you had written this year, I think, on the non-fine varieties that the living vital group is the same as this Levitch homology of
Yes. Yes, Miller K theory.
In one article I had used with other people the motivic homology group defined by Suslin Voevodsky, the CDH topology.
Yes.
Do you have the relation between them?
Yes, that's a good question. So I expect that if you replace this by something weaker, namely say the Suslin homology, then I think, but that is related with some kind of Suslin homology. It's a homology theory, but it's for open variety, it gives an analog of this kind of chalk, but weaker one, in the sense that it's related with the CDH cohomology. So then I believe that if you take either that or, as you said, the CDH motivic cohomology, which was described, I saw first time in the Hessemeyer's paper, that you have in the paper of Hessemeyer where he proves the CDS descent for KH. If you take that motivic cohomology, like namely H2D, D, then I believe that it should be isomorphic to what I said with CDH, replace CDH, Jareski or Nisnevich by CDH. But I have no proof of that. I believe this should be true.
No, because that's the thing which is functorial here in some sense.
Yeah, even this is functorial in some sense, but only difference is that that has a full theory, this doesn't. But I believe that if you take that one, then it should be isomorphic to the CDS cohomology of Milner-Schiff. But as far till now, I have not proven it.
And the CDH cohomology of the Milner-Schiff is the same as the Nisnevich cohomology?
No. It will be no, because it will kill a lot of P torsion. No, I don't think so. It will have. In fact, I should tell you that. In fact, it's known that the kernel is P torsion. For a fine variety, yes, but this theorem I am saying for any quasi projective.
So that would be the same on a fine variety?
If a fine variety, yes. If I can prove that, yes, that's right, that's true.
That would be worth to know, right?
Yeah, that will be worth knowing. I know, like, because why Elaine is asking that, because there is a paper by Elaine, Maurice Kurz and Olivier Wittenberg, where they study if you have some kind of a regular model over some discrete Henselian discrete value relation ring which has a semi-stable reduction, then they prove some kind of restriction isomorphism where they take the cohomology of the special fiber as a CDH cohomology. And I am trying to study that. I'm basically trying to generalize that where with the joint work with Federico Binda, where we are trying to remove this condition that it has a semi-stable reduction, but just take the CDH cohomology of that and replace CDH cohomology by this Levin-Weibel Chow group. And my hope is that if we do that, then we do not need semi-stable reduction. And the connection with that is what Ellen said, that you take the CDH and here you take Nisnevis.
And another tiny little question.
Yeah.
And then I stop. So you have this nice comparison theorem. I think dimension 2 was Mark Levin, or co-dimension 2 was Mark Levin. I mean, identification of cohomology of Levin.
Yes, I forgot to say, yes, thank you, yeah. In dimension 2, our algebraically closed field, this Bloch's formula is already known by Mark Levin.
Yeah.
Yes.
But do you think one can globalize this because you are
For the non-affine varieties,
yes.
I don't have, I am trying it, but as far as I see at this moment, I don't know how to prove it. It looks very complicated. I can prove if, I should tell you that, I can prove this if X is regular in codimension 1. I have to put this condition. Then I don't need a fine condition.
X is regular, not normal, but regular.
Regular in codimension 1 suffices. But if you remove that condition also, then I don't know how to prove this.
But do you think it is correct?
I believe it should be correct if you take Nisnevis cohomology, not Zariski. Yes, then I believe this should be true. Yeah, and I should also say, by the way, that this Bloch's formula for surface in singular, because I have to be correct, for singular varieties is, for singular surfaces in Mark Levin, for normal or singularity in codimension at least 2 for surface is due to Pedrini and Weibel. Yes.